In this unit, we are going to continue looking at single variable statistics. However, in the last time we looked at single variable statistics, we were looking at discrete variables. Now we're going to look at what's called continuous random variables. So let's just look at the introduction. Some situations result in discrete data. These are often whole numbers. So number of people in a class, 1, 2, 3, 4, 5, etc. Those are all discrete. We can count things that are discrete. Other situations result in continuous data over a range. Continuous data include fractional or decimal values. Continuous distributions are often the results of measurements. So we measure things like time. We don't count time really. What we do is we measure time, or we measure distance, or we measure volume. I don't know, if I'm filling up a container with water, I don't count the volume of water that's going in there. I measure it because it's a continuous flow. Think of it that way. That's the distinction, right? So discrete data we count, and continuous data we measure. And we can see that, again, there's going to be fractional or decimal values. So that's the first thing, recognizing it. That's going to present some specific problems as far as calculating probability goes if we can't just count specific numbers. And there's ways to get around it. The probability that a variable falls within the range of values is equal to the area under the probability density graph for that range of values. So that's just talking about if we look at a histogram, which we will in this lesson, then it gives us a visual of probabilities. And if we take the area underneath the graph, then that gives us all the probabilities. And if we take a section of an area under a graph, then the area that we look at compared to the entire area will give us the probability of something occurring within that area, that range. Anyway, we'll get to that. You can represent a sample of a sample of values for a continuous random variable by using a frequency table. We'll look at that. A frequency histogram or a frequency polygon. A frequency polygon, which I think I've used a little bit before now, but just to remind you, it's a segmented line that joins the midpoints of the top of each column in a frequency histogram, and it approximates the shape of the probability distribution. Okay, so we just basically, we're going to connect the dots. We're going to put a dot at the top of each bar. We're going to connect the dots with straight lines. That'll give us an idea of the shape. One other definition that I want to throw out there today is called an attribute. That's got nothing specifically to do with continuous distributions, but it is, as it says here, a quality or characteristic given to a person, group, or object. So just keep that in mind. When you're doing the homework, you might want to refer back to that if it asks about attributes. All right, so let's look at, I've got 3 examples, so let's just jump right into the first one. Determine the number of siblings for each member of the class today. Create a frequency table. Determine the probability of each number. Graph the probability density histogram and frequency polygon for this attribute. All right, so here is, since I don't have an actual class in front of me, here is a class that I've had in the past. And so I'll go through, I ask each person in the class, how many siblings do you have? Turns out that 2 of them said they had no siblings. They're only children. 6 said they had 1 sibling. 9 had 2. 5 had 3. 3 had 4. And in this particular class, none of them had 5 or more. That's what I've already filled in this table. So if we want to get the probability, if I was to randomly pick someone in this class, and I want the probability that I get someone who had 0 siblings, well, then I can calculate that, right? It's the number of successes, or possible successes, divided by the total number, which means that I have to know the total number of people in the class. I get that by adding up the middle column. 2 plus 6 plus 9 plus 5 plus 3 plus 0 equals 25. And then I can get the probability of again, choosing, say, a person with 0 siblings by taking, there's 2 possible successes there out of 25 people I can choose from, that works out to 0.08. So there's about an 8%, exactly an 8% probability that I would choose one of those people. So respectively, if there were 6 people, well, then it would be, one person is 4%, so I can multiply 4 times these different numbers. So 6 times 0.04 is going to be 0.24. So there's about a 24% chance that I get someone with one sibling. 9 times 0.4 is 36%, and 20%, and 12%, and of course 0%. So those are my respective probabilities. So then to make up a histogram out of this, I've already got this set up a little bit for us. Our random variable is the number of siblings, and I've got the 0 through 5 plus. I put 5 and greater as a single bar we're going to represent that with. Probability goes on the vertical axis. So I see my highest probability is 36%, so it looks like if I go up like this, then I should be able to fit everything on there. So 8% would be a bar that, for 0 siblings, a bar that comes up to here. Sorry for the shaky hands, too much coffee this morning. 1 sibling, that's 24%. 2 siblings, 36%. 3 siblings, 20%. 4 siblings was 12%. And then we had no siblings for 5. No people with 5 or more siblings in this group. So just color this in so it pops out a little bit better for a visual. There's my histogram. All right, so that's the first part. I've created a probability density histogram. I get a quick view of what's going on with my class. To change that into a frequency polygon, that's where I put a dot at the top of each bar, and then I connect the dots. And I'm going to put a dot here at 0 for 5 plus, and in fact I'll just start here just to help me see the shape a bit more. I'm going to connect all of these with relatively straight lines. I'm not using a ruler, I'm just getting a general idea. So that gives me a pretty good idea. That looks like a pretty normal distribution. We've discussed normal distributions before, and it's one that's sort of bell-shaped, which you can see this one is. Is this data discrete or continuous? All right, so getting away from the histogram for a minute, let's just think about the data. So in other words, number of siblings, am I counting that or am I measuring it? Another way of looking at it is it whole numbers, 1, 2, 3, 4, 5, or is it decimal or fraction numbers? Because if it's whole numbers, it's discrete. If I can break it down into decimals, then it's continuous. And hopefully, pretty clearly, we're going to count this one. Number of siblings is discrete. We're counting whole numbers. What's the total area of the rectangles of the histogram? Well, if we add up all the different probabilities for each bar is 1 unit wide, and if I add them all up, then the area is going to be the different probabilities I had. So 0.08 and 0.24 and so on. When I add that all up, it better add up to 100%. I could add a 0 here on the end. Obviously that won't make a difference mathematically, but at least it feels like I've included the 5 plus. adding those all up, so you can do a bit of mental math, and yeah, it definitely adds up to 1, or 100%. That's what we expect. Alright, so there's just something that we've already done this. This is not new because it's discrete. We spent pretty much a whole unit talking about discrete probability distributions. So this isn't new, although using the frequency table, the frequency polygon, we've got a couple of new concepts in there, but this isn't brand new to us. Here's something, though, that is going to be new to us. Example 2. Chris works at a tire store. He can change a tire on a rim in 8 to 12 minutes. So the quickest he can do it is 8 minutes. The longest it takes him is 12 minutes. You know, there's obviously various variables involved, like how easily the tire comes off due to whatever. All right, so with all times in between equally likely. That is important. All times in between are equally likely. So, sketch a graph that illustrates this distribution using time on the horizontal axis and probability density on the vertical axis. So I've already started to set this up a bit. So this is time in minutes that I've set up here. Now, what I need to do, the first thing that I have to do that's going to be different now that we're dealing with continuous, and I guess I didn't specifically say this, but we are dealing with a continuous probability distribution. Why is it continuous? Well, think about that for a second while I write this out. It's because time is measurable. It's not countable. Measurable. Another way of thinking about it is, it does make sense to have fractions of a minute or decimals of a minute. I can have a minute and a half and it makes perfect sense. It doesn't make sense to have 1.5 siblings. I could have 1 3/4 minutes. I could have 8.1 minutes. I could break it down smaller and smaller. It's a continuous flow. Time just keeps flowing. So this is a continuous probability distribution, which then means, how am I going to graph it? The first thing I'm going to have to do to decide to graph it is I'm going to have to come up with intervals. I need to decide on how big an interval I'm going to have. Use 1 minute intervals for this case. So that's not always going to be the case, but in this example, let's break things up into 1 minute intervals. All right, so all the times that it took him to change a tire in 8 to 9 minutes would go together. All the time it took him from 9 to 10 minutes would go together. You know, sometimes, let's take the first example, 8 to 9 minutes. Maybe one time in his fastest possible time it takes him 8 minutes. Maybe another day when he's really good but not quite as fast, it takes him 8 minutes and 13 seconds. Another time maybe it's 8 minutes and 47 seconds. Another time it's 8 minutes and 59 seconds. All of those times are in the 8 to 9 minute range. So we're going to group them together. That's what I mean by an interval. As soon as you hit 9 minutes, then we're bumping up to the next interval. So then you got the 9 minutes, you got 9 minutes and 5 seconds, you got 9 minutes and 7 seconds, you got 9 minutes and 17 seconds. Anything in the 9 minute to 10 minute range would fall in the next interval. So how many intervals are there? Well, we got 8 to 9, 9 to 10, 10 to 11, 11 to 12. I count 4 intervals. So the probability that a time for any given tire change is going to fall in a particular interval, since they're all uniform, right? They're all equally likely, means that I would take the 100% probability divided by the number of intervals, which in this case is 4, and it means that there's going to be a 25% probability that it will fall in any interval. So there's a 25% probability that it'll take him somewhere between 8 and 9 minutes, a 25% probability it'll take somewhere between 9 and 10, and then 25 for 10 to 11, another 25% for 11 to 12. That covers all possibilities. So there you have it. That means that this is a uniform probability distribution. The highest probability is going to go up to 25%. So again, let's just put my scale like this. That'll work. And so the lowest time is 8 minutes. So I can ignore that 7 that I've already put there. You can't have a tire change in less than 8 minutes from what we've been told. But there's a 25% probability that he is going to change a tire between 8 to 9 minutes. There's a 25% probability he's going to change a tire between 9 and 10 minutes, and a 25% probability between 10 and 11. So this should be perfectly flat across the top, if I could draw it that nicely, because they're all supposed to be exactly 25%. This is our probability distribution. Now what you'll notice, which I haven't really discussed yet, is that no longer am I putting a number right underneath a bar, right? For example, for 2 siblings, I put that number in the middle of the bar and then just had it arrange, or the numbers, it went from a lower side to an upper side with that 2 in the middle. When we're dealing with discrete probabilities, where are we? Here we are. When we're dealing with continuous probabilities, continuous probabilities, we need a starting point and we need an ending point. So the starting point for the first interval was at 8. The ending point for that first interval was at 9. Any time that fell between 8 and 9 went in that bar. So I put the 8 and the 9 on the edges of those bars. So that first bar is literally going from 8 to 9, and that's why the numbers are right there on the edges. The next bar is literally going from 9 to 10. That's why those numbers are on the edges. I don't have to write the 9 down twice, it's just on the dividing line. And so that's why, again, we have histograms have the bars pressed up against each other to show that there shouldn't be any gaps in between. 8 to 9, 9 to 10, there's no in between those two. It just runs together. All right, what kind of distribution is this? I already said it's a uniform distribution. And that's because all times are equally likely. That's what you get when they're all equally likely. What's the probability that Chris changes a tire in less than 9 minutes? Well, less than 9 minutes, if we look at our graph here, let's just draw a line here. So here's the 9-minute mark, and he can't go less than 8 minutes because he just doesn't work for him. He's not that fast. So basically saying it's less than 9 minutes means it's between 8 and 9 minutes. Well, we've already seen that between 8 and 9 minutes for Chris there's a 25% probability of that. Okay? So let's get rid of that marking. So I would write that as P at x is less than 9 is equal to 0.25%. Because it's 1 bar on the graph. What's the probability that it takes him between 9 and 11 and a half minutes? All right, let's look back at the graph. Here's 9 again. 11 and a half would fall halfway between 11 and 12. we want this much of the graph. Remember, the area that we are looking at also corresponds to the probability. So what percentage of that graph that I've colored in yellow has now been changed to green? Well, if each bar is 25% of the overall graph, I can see that I've got 2.5 bars here. 9 to 10 gives me 25%, 10 to 11 gives me 25%, half of 11 to 12 gives me 12.5%. All right? So I could write that as the probability that x is greater than 9, less than 11.5 is equal to 25% for 1 bar times the 2.5 bars, and as I already pointed out, that equals 0.62. I didn't add it up for you, I guess, but it adds up to 62.5%. 25 plus 25 plus 12.5. What is the probability that it takes exactly 10 minutes for him to change a tire? Okay, now we get to something interesting. Let's see. Can I delete this? It's going to become hard. Maybe I won't try to... I was going to delete my shading from the previous example, but that'll get rid of everything. So, let's just look at this. I'll do it in red. Here's exactly 10 minutes. I'll draw it as a solid line. So this red line is 10 minutes, as you can see. It's a line. What is the width of a line by definition? How much area does a line have? The answer is that a line actually has no area. There has to be 2 lines with something in between it. A line has no area whatsoever. So how does that affect our answer? Well, if it has no area, that means that the probability must equal 0. But I can imagine people thinking, how is that possible? How could the probability be 0? Obviously, there is a chance that it takes him exactly 10 minutes to change a tire, so it can't be 0. And you're right, but the thing is that mathematically it's 0. And the reason is because it's actually so small that we can't even calculate it. Let's go back to our formula. Remember, P at x is equal to number of successes, number of ways to be successful, divided by total number of ways of doing things, total outcomes, total possible outcomes. Okay. Well, obviously, yes, it could take him exactly 10 minutes to change a tire. So there's one way of doing that. But how many possible outcomes are there? This is where it gets interesting. If it's continuous, and we can break the numbers down and break them down and break them down for an infinite number of ways, then there are actually infinite possible outcomes. We can just keep cutting up those time sections smaller and smaller. If we divide 1 by infinity, then basically what we get is 0. Again, it's not exactly 0. Well, I don't know. Now we're getting philosophical. I'm going to say basically 0 anyway. There's no bar, there's no width, there's no probability. So for our purposes, for anything that's continuous, and so we're going to extend this beyond this example, for any continuous distribution, the probability of getting one exact value will always equal 0. Last example, all right? And this one is going to, well, actually, let me read it first. Many businesses use arrays of lights to attract customers. The life of a light bulb follows a continuous distribution, right? Because the life of a light bulb is a time, and time is continuous. A sample of 40 light bulbs that were tested, and the lifetime of each does not make sense. Anyway, let me reword it to make it make sense. A sample of 40 light bulbs were tested, and the lifetime of each bulb is in the table below, rounded to the nearest day. Alright, so it's rounded to the nearest day. So again, it's continuous because that's what time is. But if it's rounded to the nearest day, it's sort of like we're making it discrete. But even then, rounding it to the nearest day, right, we have to have intervals. Just like we had intervals here. We used 4 1-minute intervals for example 2. For example 3 here, I don't want to have a different interval for each day. The shortest time, and I'm just casting a glance over it now, let's see, 133 days, I don't see anything shorter than that, but let's say that's 133. The highest number of days that one lasted was, I see, 171, anything better than that, 172, 175, anyway. I don't want to have one interval for 133 days, and another interval for 134, and another one for 135, all the way up to 175. That's too spread out, too much work, and actually not much help. So we're going to group them together, even though they're already somewhat discrete, into bigger intervals. We're going to put the intervals in groups of 10 days. So 130 days to 140 days, as I've already done here. And then 140 days to 150, and so on. So I've got 10-day intervals going on. You may notice something funny happening, though, with the brackets. There's a square bracket I put on the left and a round bracket that I put on the right. I've written below already what that stands for. The square bracket means include the number beside it. The round bracket means up to but not including the number beside it. The reason we have to do this is so we don't have overlap. So let's look at the first one. 130, 140, square bracket beside the 130, round bracket beside the 140. So the way I'd interpret this is to mean that if a light bulb lasts exactly 130 days, then I'm going to include that. If a light bulb lasts up to, but not including 140 days, I'm going to include that. Put this a different way, I've got 140 written down twice. You can see I've highlighted in blue. If something lasts exactly 140 days, according to my table, which interval do I put it in? Do I put it in the 130 to 140 or the 140 to 150? The round bracket tells me don't put it in that interval. Anything up to 140 I'll include, but the 140 itself should go in this interval because it's got the square bracket beside it telling me to include that one there. So that allows us to, again, do a short form just using different types of brackets without having to explain it each time. In order to save a bit of time, I did a tally table already, so basically went through and did, okay, 163, that goes in this one here, and 152, that goes in this one here, and so on. So I've already done the tally table for you. I'm not going to redo it here, but that's where the tally table came from, or the tally in the table came from, was one by one crossing off these numbers and doing a little tick mark in the appropriate interval. So then we know the frequency just by adding things up. 8, 13, 11, 5, and 3. Okay, so we can put things that are discrete into histograms if we put them into intervals. And again, this isn't discrete, but because we've rounded to the nearest day, it's kind of like it is. It's sort of this in between. But anyway, we can do it. We can still put it in an interval. All right, draw the frequency histogram, add the frequency polygon. So I've already started this again. So because we're using intervals, I've put I put the numbers on the edges, or I'm going to put the bars between the numbers. So in other words, from 130 to 140 had a height of 8. And maybe I'll go up by 2s. So 2, 4, 6, 8, 10, 12, like that. So between 130 and 140, we had 8 bulbs that lasted that long. And then 140 to 150 had 13 bulbs. So that would be, I'm going up by 2s, right? So that would go here. And then 11 for the next interval. And then 5. And finally 3. So there's my histogram. And then I can make a frequency polygon out of it. I didn't draw the dots this time, but I can imagine a dot at the top of each bar, so it's easy enough to connect my imaginary dots, and I can put them there if I want to. So there's my frequency polygon. How is the shape of the frequency polygon related to the frequency histogram? Well, it shows the shape. It lets us see what the shape of the frequency histogram is. It shows the shape, let's say, of the distribution. What type of distribution is this? Well, we've seen some different types of distributions. One that has a higher bump on the the left-hand side, and a tail on the right is called right skewed. And that is an introduction to some of the concepts we're going to look at for continuous distributions.